This video is about simply supported beams, which you have to study as part of your mechanical principles unit. Okay, so here we can see an example of a simply supported beam. I'm sure you're all familiar with Stonehenge. Okay, if we look at different beams types, they can be classified into different groups. So here we've got cantilever, which is it's supported at one side only. Simply supported, so we have two supports here and here, and these are the ones. This is the one that you're going to be doing calculations for. We have overhanging. We've also got continuous, fixed end, and cantilever with simply supported. So if you're on to higher level education, you would probably study some of these extra ones like cantilevers or continuous. But for your course, you're looking at simply supported beams. Now, if we look at some examples, here we have an aircraft wing. Hopefully you can see that the support is here, and there is no support at the other end, so that makes it a cantilever. Okay, we've got low pressure above the wing, high pressure below, so that means that all along here we have air pressure acting up on the wing, which lifts the aircraft up. Okay, so that would have the force applied over the bottom of the cantilever by the air. Here we have a stadium roof, and this is commonly used as a cantilever because if you're in the crowd, you don't want to have a lot of supports at the other side because they would block view. So they're quite complicated structures, and the load comes from the weight, mainly the weight of the steel. So you'll have the load acting downwards on this cantilever. It'll also have to support any rainwater on top, and if it's snowing, the snow will lie on top of it and add more weight. So the design would have to account for that. Okay, so on this cantilever, we would have loading on the top of the cantilever. So on the cantilever, we can load on the bottom or the top. Okay, here we have an example of a fixed end beam. So this could be a bracket in a say a desk or a set of shelves pinned at either end. So we've got supports fixed here and here, and we can have a load in the middle, or we can have a load all the way along. Just depends how it's loaded up. And you can see that's very simple. It's actually a fixed end. Both ends are fixed completely. We looked at Stonehenge briefly at the start. So here we have these capstones here are the beams, and they're supported by vertical stone beams. Okay, so the two supports are here, and the load is because of the massive weight of the stone downwards. Okay, so you can see here, simply supported beam. It's not fixed at either end. It's just resting on top of the supports. So that's what a simply supported beam is. It's a beam that rests on top of two supports. Now in engineering, we tend to look at point supports, so that we can actually have the force acting through the support force acting through a sharp point. But here, with this type of beam, this stone beam, the support acts across a certain amount of the beam. Okay, but in your examples, you'll be treating it like a point support. Here we have another example of a simply supported beam, a complex bridge structure. Now, if you take the whole lattice structure, okay, as being the beam, all right, it's actually a complex structure, but if we treat it as one long structure, hopefully you can see that we will have supports on these columns, and the beam will span across a gap, allowing a road or a railway or whatever to go across the river. And again, the loading will be along the whole length of this. Okay, so due to the weight of the steel in the massed beam, there will be constant loading there. We'll also get point loads occurring. So say it's a vehicle bridge. If a lorry goes over it, there'll be as the lorry goes along, wherever the lorry is, it'll be a point load. You might have some cars, a bus, whatever. So you'll have point loads as well. So this brings us on to symbols, and we'll be looking at in a slide, in a couple of slides. Here we have an overhanging gantry crane. So here we've got our supports, point supports, and you can see them here and here. Okay, and this is the crane, so it can actually move in between, or it can come out to here and pick up loads. So because it's overhanging, we have these two overhanging, or we can have one side overhanging and the other side not, but in this case they're both overhanging, so that's an overhanging type beam. Okay, so in terms of symbols, with beams we can have different types of loading, and here we have a UDL. Now that's short for Uniform Distributed Load. Okay, so Uniform Distributed Load, and that just means a load spread along the edge of the beam, sorry, along the top of the beam. Now in real life you could have a UDL acting on one section of the beam, but in most cases the beam will have a UDL across the whole length of it, because the beam itself will have a certain amount of weight, and that will be divided up between its length. Okay, UDLs are spread across the section of the beam, in this case the entire beam length. UDLs are stated in newtons per meter or kilonewtons per meter. So for this UDL we might have, say, 10 kilonewtons per meter. Okay, now if this beam is 15 meters long, we'll say 10 meters long, every single meter of that beam will carry 10 kilonewtons. Okay, so if we have 1 meter here, 10 kilonewtons will be acting on it. The next meter, 10 kilonewtons will act on it, and so on. So in total, the total load from the UDL with this beam will be 10 times 10. Okay, 10 meters times the 10 kilonewtons, or 100 kilonewtons in total. We can also have point loads. So these are loads which just act at one point. So this could be 200 newtons or 200 kilonewtons, 50 kilonewtons. Okay, so those could be stationary objects, or the leg of a piece of steelwork coming down and sitting on the beam. So they are applied at one point. So very first examples we're going to be looking at are beams with point loads only, and that means that they're simpler, so you can get your head around how to do the calculations. So whenever you get a question, you may have a complicated diagram like this, and you don't need to draw this out again. You basically just draw a line for the beam, okay, and an arrow for the supports. So we're going to call the supports R for reaction. Okay, so when we have a downwards force, we have a reaction from the beam, so that's why they're called R. Now we have to differentiate them, which means we have to tell them apart. So you can either call them RA and RB, or I kind of prefer RL and RR. So the left reaction and the right reaction. Okay. We also draw our forces on. So Here's our 50 newtons and our 200 newtons. And we can put our distances on 3, 4, and 2. Okay. So I'm just going to do that again on the slide, next slide. Okay, so we have our reaction, our beam, our two forces, RL, our R, 50, 200, and our distances are 3, 4, and 2. Now, when we're looking at beams, we're thinking about turning moments and forces. Now, in our non-concurrent force systems before, we had to make sure that the forces were balanced. And in this case, it's even more so, because with a beam, we don't want it to rotate, we don't want it to move. So, for the beam, the total anti-clockwise moments will equal the total clockwise moments. Now you can do that shorthand. You can say anti-clockwise moments equals clockwise moments. Use symbols. Okay, same thing. So if we look at this picture, which ones are trying to turn clockwise and anti-clockwise? Well, the first thing we need to do is to pick a pivot point. Now we could pick a pivot point anywhere along that beam. Okay, so we could pick one there. And if we took moments about it, the moments clockwise would equal the moments anti-clockwise. If we picked another point, say here, the same thing would apply. All the clockwise moments would equal the anti-clockwise moments. But picking them in the middle of the beam doesn't really help us, because we've got two unknowns. We've got RL and RR. Okay, so we want to try and get rid of one of those. And the way we do that is we use the fact that if we take the moment about one end or the other, the reaction force will act through that point, and therefore that force will not have a moment. Okay, so I'm going to take my moment through the left hand side, so I get rid of RL, because the distance of that force from that pivot is 0, so RL times that force is actually 0. If we look at this here, these are going to try and turn the beam clockwise, and RR is going to try and turn it anti-clockwise. So anti-clockwise on the I've said anti-clockwise on the left of the equation, so I'm going to do that here. So our force is RR times our distance, which is the total distance from the pivot point. So that's 2 plus 4 plus 3. So 2 plus 4 plus 3. I'm just doing it. I could just have written there 9. Okay. And then we've got the two forces, 50 times its distance to the pivot plus our 200 times its distance to the pivot point. Now you can see here that the 50 is 3 meters from the pivot point, and the 200 is 4 plus 3, the total distance to the pivot point. So that's 7. So we have got 9 RR equals 150 plus 1,400. Okay, so 1,550 equals 9 RR. So RR equals 1550 over 9. So RR equals 172.2 newtons. Okay, so I just need to continue this on in video 2. I'm running out of time for the maximum recording size.